Okay, let's start. Good morning. So I'm very happy with the results of the second midterm. The average is around 91, I think. So it's pretty good. With that, we're now switching over to the sort of the meat and potatoes, really, of this class. The next 3 weeks is going to be rather heavy in these new concepts, in a sense. In a sense, they are not new, but it's going to take a while, I would assume, I would guess, to get accustomed to. And this is really also the most useful part of basic linear algebra. So, and our topic for this week is spectral theory. We're going to do something else next week. We're going to start talking about orthogonality, and then we're going to go back to spectral theory and do some more of it. So the reason why there's this word spectral or spectrum you could see here has to do with ultimately this physical phenomenon that then you have this white light. If you make it pass through a diffracting prism, you can split it into its components. Okay, and this does happen, and through some, let's say, physical developments, eventually people realize that somehow this idea of being able to split light into its components has a mathematical has something that has a mathematical corresponding concept, which is a spectrum of an operator or a matrix. And so this week is going to be all about understanding this, starting with a matrix and splitting it essentially. And so here are the definitions. I start with an n by n matrix that is with real entries. Its eigenequation, okay, is this equation. AV equals lambda v. Lambda here is a complex number. V is a complex vector. I want it to be non-zero because if it were zero, it would be satisfied for no matter what lambda is. So here, this lambda number is analogous to one of these colors, essentially. In this case, if you can solve this equation, lambda v, so they come in pairs this way, they are coupled to each other in a sense. They are called an eigenpair for the matrix, and lambda is called an eigenvalue, and v is called an eigenvector. And if I were to take all these numbers, lambda, and put them in a set, that's called the spectrum. Okay, so this is just a bunch of definitions. Let's immediately switch over to examples. And as usual, we start with 2 by 2. So let's consider this. Okay, now I want to understand all of these things associated to A. I want to figure out the eigenvalues of A, eigenvectors of A, the spectrum of A, and so on. I should also mention here, I wrote here C, but really what we want is real numbers and real vectors. Sometimes it happens to be the case that you can't really find solutions to this, but if you're just using real numbers, so that's why we're using complex numbers there. So the eigenequation for this is like this, right? So and let me write this out even further. I can write it like this. Maybe even like this. Now, the issue here is that here, both lambda and xy are unknowns. So this is so in this equation, I have 3 unknowns. And you see, I'm multiplying 2 of the unknowns here, and likewise here. In linear algebra, we never multiply unknowns, okay? So somehow we need to sort of like do something about this, because ultimately I would like to be able to use linear algebra to solve it, both for lambda, and x, and y. So I need 3 numbers, essentially, as the solution to this eigenequation. So instead of doing it like this, one can think of it like so. Now, instead of writing lambda times xy, I'm going to think of lambda as identity times lambda, right? So because this I can write like this as well. Sending, let's say, this to the other side, and then consolidating, we have this. So lambda 0, 0 lambda, xy, minus 3 minus 2, 1, 0. xy equals 0, 0. And then collecting these terms, I get this. Lambda minus 3. Here I have 2. Here I have minus 1. Here I have a lambda. Okay? So somehow all this business allowed me to put one of these unknowns into the matrix itself, into the coefficient matrix. Now what I'm going to do is I'm going to pretend that this lambda is unknown, but also it's sort of like a parameter. And I'm going to try to do row reduction to solve for x and y with lambda as unknown. Okay? So let me do it here. So the augmented matrix of this is like so. So think of lambda as a parameter. So let me write it like this. Think of lambda as a parameter and do row reduction to find the solutions x and y with respect to lambda, of course. And do a row reduction. Okay, so if I augment my matrix, augment my matrix, I get this augmented matrix now. So how can I do row reduction with this? Any ideas? Essentially, I want to get rid of entries. So what should be my first step?
I guess you could multiply the second equation by lambda minus 3 and add it to the first one.
Right, so you can say, oh, you know, up to some multiple, I can use this to get rid of this. The reason that's a good choice, as opposed to taking this and getting rid of this, is that you don't know what lambda is. So maybe lambda is 3, in which case this is 0, and you cannot really get rid of this. But no matter what lambda is, using a multiple of this, of the second row, you can always get rid of this. Okay? Even if it were there, right? So that's the second row. And what I want to do is, so the first row is this. I want to multiply the second row by lambda minus 3. So now I have this. And here I have lambda times lambda minus 3. Here I have 0. If I were to add these up, you would get here 0. Here I would get 2 plus lambda times lambda minus 3. Here 0. Okay, so this is here. Maybe I should write it larger. And here, this is lambda, this is 0. At this stage, you can try to keep beautifying, let's say, this matrix. But let's just first focus on this entry here, because we can rewrite this like this. I just expanded this product, and it gave me this. And then I can split it further, right? So this is equal to lambda minus 2 times lambda minus 1. Okay? So now focus on this first row. Unless this entry is 0, this system would be inconsistent, right? Because this is 0, which means that in order for this equation to have a solution, that is to say, in order for this equation to have a solution, it must be the case that if you have 0 on the right-hand side, every other entry is also 0. Okay? So let's write it here. Star. In order for star to have a solution, non-zero solution, of course, I'm looking for a vector xy that is non-zero. Okay, I want a non-zero vector. Let me perhaps write it like this. Have a non-zero solution. It must be the case that this is 0. So this is 0. In other words, either lambda is going to be 1 or it's going to be 2. Otherwise, it doesn't have any non-zero solutions. Okay? If lambda is 1, now I do a case analysis. Either lambda is 1 or lambda is 2. Well, I can just plug in, right? Plugging in, I get this. In this expression, minus 2 to minus 1, 1. xy equals, or maybe I should have put it over there. Let's do it that way. So in that augmented matrix, I plug in lambda equals 1, and I get this. The first row I know is going to be just zeroed out. The second row tells me something. It tells me this, minus 1, 1, 0. Now this is the x, so this column is the column that corresponds to x, and this column is the column that corresponds to y. So the solution to this is minus x plus y equals 0. Or maybe I should write it like this, x equals y. X equals y, y free. And in particular, I have that, let me write it like this, v1, and let me call this lambda 1. v1 equals 1, 1. Okay? Now, all this really tells you that 1 together with 1, 1 is an eigenpair. It's a solution to the eigenequation. In other words, 1 is an eigenvalue for A. v1, which is 1, 1, is an eigenvector of A associated to the eigenvalue 1. Okay? So let's check it. If I were to apply A to this vector, I should get back itself, right? So A times v1 is the same thing as 3 minus 2, 1, 0, 1, 1. And of course, when I multiply this, I get 1 here, 1 here. So this is 1 times what I put back in. So everything is good. Now, we're not done, because the other case is when lambda is 2. And lambda is 2, I need to do the same thing. Okay, I'm going to plug in lambda equals 2 into that augmented matrix, which gives me, again, 0, 0, 0 here. And now, you see, this gives me minus 1, 2, 0. What are the solutions of this? Minus x plus 2y equals 0. In other words, x equals 2y. Let me write it like that. And again, y is free. And for this, I can just pick the simplest one. Let me choose y to be 1 so that x is 2. Now this, you see, is another eigenpair. Lambda 2, which is 2, is another eigenvalue, and corresponding to it, here is an eigenvector. And again, we can check. If I apply A to V2, I get this. So now it is 6 minus 2 is 4, and then 2 plus 0 is 2. This is twice the input. Okay? Any questions about this so far? Let's keep going. Let me write down what I said. So, or let's continue writing things down. So what is a spectrum? Spectrum is a set of eigenvalues. So it's a set of numbers. One is 1, the other one is 2. So I would write it like this. This is unordered. And really, I want to think of the spectrum as a certain subset of the complex plane, of the space of complex numbers. And so I would write it like this. Maybe I should draw it like so. One of the eigenvalues is here. And then the other one is somewhere here. Right? One is 1, the other one is 2. This is a spectrum. Okay. Now, eventually, we're going to realize how to split concerns again, how to separate the concerns. Computing lambda is going to be one thing, and computing the eigenvectors is going to be another thing. But for now, as you can see, again, we can apply row reduction. Perhaps it is slightly more complicated because this time, in order to apply row reduction, I really need to think of this as a parametrized matrix, but still, it works out. So let's keep going. This is the picture of the spectrum. But I want to think of A itself as well. So allegedly, this spectrum of A should tell me things about A. Right? It should tell me, it should allow me to decompose A in a certain way. And so here's the picture. So one vector that we came up with is 1, 1, and the other vector that we came up with is 2, 1. Okay? So let me draw them. This is the first vector, and the second vector is somewhere here. Let me, in fact, draw them like this. Okay. Okay. This is V1, this is V2. Now, V1 is an eigenvector of A associated to the eigenvalue 1. Right? This is what we computed here. In other words, if I were to apply A to my vector V1, it's going to stay at the same place. And this would be the case no matter what eigenvector I choose for lambda equals 1. So for instance, 2, 2 is also another eigenvector. It satisfies the solution after all. And if I were to apply A to 2, 2, I would get back 2, 2 again. In other words, not only is this V1 associated to lambda equals 1, but indeed this whole span, the subspace of the plane spanned by the eigenvector, is associated to lambda. And if I try to visualize how A operates, I would say this. So if I stay here, so if I start here, A is going to keep, so if I apply A, any vector on this blue line is going to stay where it is. They're not going to move. Okay? On the other hand, if I were to take a vector along the red line, which is a span of V2, now you see, if I were to apply A to V2, I get back twice it. Okay? Which means that along V2, A is operating as a stretching by a factor of 2. So this is A times V2, and then A squared of V2, and so on. So A is fixing any vector on the blue line, and A is stretching the whole red line by a factor of 2. Okay? Yeah, yeah. Mm-hmm.
Okay.
Yeah.
It's not like V1 where it's just, or is V1 as well where each position is a squared or a cubed?
You can think of it that way, but because A times, so A of V1 is V1, A squared of V1 is also V1, and so on. So there's no really point of writing it. So if you want, perhaps I can write it like this. So maybe like this. Okay. So under A, any vector in the blue line is fixed, and any vector on the red line is stretched by a factor of 2. It escapes the origin. And in a sense, this spectrum is already telling you this. This circle is supposed to be the unit circle. You see, this eigenvalue is on the unit circle. This is really signifying that so if any vector is an eigenvector for this eigenvalue, A is fixing that. But this is outside the unit circle, which tells me that A is expanding this vector. Okay? Under A, under iterates or powers of A, any eigenvector outside here, or any eigenvector corresponding to an eigenvalue outside the unit circle, is going away from the origin. Okay. Now let's also think about this. Once I plug in an eigenvalue here, this is just a standard matrix, and I'm really looking at the null space of that matrix. Okay? That null space is called the eigenspace associated to the eigenvalue lambda. So the null space of lambda times identity, that's what I did over here, minus A, which is a matrix after all, is the eigenspace of A associated to lambda. Okay? Any questions about this? Okay, let's do another example. Yeah.
For the lambda values,
Yes.
are they like constants or are they vectors?
They are numbers.
So with your like illustration,
Yes.
it feels like you're never going to escape the x-axis, you know, for your like lambda values.
Oh, you mean in the picture for the spectrum?
Yeah.
Well, think of a rotation.
Think of a rotation.
Yeah.
I guess what would the lambda value, like how do you ever not live on the x-axis? Like, because you said, you know, the fact that your lambda value is 2, it tells you that whatever vector is going to get twice as big. What lambda value would correlate to like a rotation?
Yeah, so for instance, consider rotation by 90 degrees. Geometrically speaking, being able to find an eigenvalue corresponds to, or being able to find the real eigenvalue corresponds to being able to find a line that is invariant under your matrix. So in this case, I was able to find 2 distinct lines. But under a rotation by 90 degrees, there is no such line. Okay, because everything is being rotated. Still, complex numbers are invented for this. We have imaginary values that we can use as eigenvalues. We'll get to that.
Oh, so I guess maybe the y-axis doesn't correlate to like reals. It's like the imaginary unit.
Yes, yes, yes. In this picture, in the left picture. So this, let me say, this is the complex plane. No. So this is the real R2, and this is the complex plane. So this is like the x coordinate and the y coordinate, or a plus ib. So in this case, these two are real numbers and that's why I put them on the x-axis. Now, once you start looking into infinite dimensional operators, or operators on infinite dimensional spaces, this set that we call the spectrum turns out to be much more complicated. In our situation, it's always going to be a finite set. But still, it's good to sort of like be able to draw the spectrum of a matrix. Okay, so here's another example. Now my matrix is 1, 6, 5, 2. I'm going to go through the same thing, okay? So let me just fast forward this stuff, and already let me start from there. So I have lambda, this parameter on the diagonal, and then I'm going to subtract the entries of A. Minus 5, minus 2, and then I augment it. Okay? I fast forwarded all this to over there. It's the same idea. Okay? I don't know what lambda is. And also, let me mention, in this previous case, initially we had this situation that maybe at that stage lambda was 3. And that's why we couldn't use it. But ultimately, when we computed things, it turned out that lambda is not 3. So right from here, I cannot just say, oh, one of the eigenvalues is 1, and the other one is 2 or something. It doesn't work that way. You need to go through the row reduction. So what do I need to do? I can take the second row, and if I were to multiply it by an appropriate number, then I would here have minus lambda plus 1. So let me write it here. This is the first row, and then the second row I want to be this. So 5 times divide by 5 and multiply by lambda minus 1. So that's the factor. So if I were to multiply the second entry by this, I get this. Okay, so that means that, so this is now minus this, so I need to add. If I were to add this to that, I get this. Minus 6, and then this. Plus lambda minus 1 divided by 5, lambda minus 2, 0. And then here I have 1. Oh, this is 0, of course. And then I have, let me just leave the second row as is. I don't really need to worry about it. Okay, now that we're done with this, the obstruction again is this term. So I need to expand it and figure out what the zeros are. The zeros here, so whatever lambda values that make this expression 0 is going to be my eigenvalues. So I need to expand it. So minus 6 plus lambda minus 1, lambda minus 2 divided by 5. I want this to be 0. In order for that to be 0, if I were to consolidate everything, I could get rid of this denominator. And so that would be minus 30. This has to be 0. Now this is lambda squared minus 2 lambda minus lambda gives me minus 3 lambda. And then plus 2 minus 30 gives me minus 28. Now 28 factors as 7 times 4, and that gives me the factors. Or, you know, we could use the quadratic formula or whatever you want to use. Okay? Now, the same story, I have two distinct eigenvalues, you see. One eigenvalue is 7, the other one is minus 4. Again, I need to do a case analysis. Let's say lambda 1 equals 7. And then I'm going to plug in lambda equals, or lambda 2 equals minus 4 somewhere else. Instead of using this reduced echelon form, or, you know, reduced form in some sense, I can just go back to the original equation. Often that is much simpler. So if I were to look at this matrix over here, I would get this, right? So 7 minus 1 is 6, 6, and then 5, 5. xy equals 0, 0. Now the eigenvector, one eigenvector that I can use is this, 1 minus 1. Okay. Well, minus 1, you can just eyeball at this stage for a solution to this. Okay. So that's an eigenvalue and a corresponding eigenvector. And doing the same thing with the other eigenvalue, I get this. So minus 4 minus 1 is going to be minus 5. Oh, I made a mistake.
Where did 6655 come from?
Yeah, okay. Sorry, made a mistake there. So I should write it like this. 7, 7 on the diagonals, and then I need to subtract the entries. Minus 5, minus 2. Does this work now? I changed the numbers. So I have lambda times identity minus a. That was sort of, you see, that's that matrix over here. So now this is 6 minus 6, and 5 minus 5, 5. So instead of plus here, I should, minus here, I should put a plus. Now it should work. Are we happy now?
How did you get the 1, 1?
I just eyeballed it. Okay. I mean, a solution.
So are we trying to figure out what x, y is?
Yes.
Oh, okay.
Yeah, yeah. Yeah. And the same thing here gives me this. And then minus 1, minus 6, minus 5, minus 2. You see now it is slightly more complicated, but it's again nice because the second row is the same thing as the first row. Once you plug in an eigenvalue, this matrix is always going to have rank less than the maximum. In this case, it's going to have rank 1. So this is minus 5, 6. And so what I can do is I can use, for instance, if I put here 6 minus 5. Okay, let's check it. So 1, 6, 5, 2 multiplied by 6 minus 5. And that gives me 6 minus 30 minus 24. 30 minus 10, 20. Okay. So this is, so I can factor out this minus 4 to get back 6 here and minus 5 here. You see? It is indeed an eigenvector associated to the eigenvalue minus 4. And likewise, you can check over there.
So when we see our m values, our expectation is that matrix A, whenever it acts on a value vector, with lambda 1 it'll be 7 times bigger. With lambda 2 it'll be minus 4 times bigger.
Exactly. Yes. Insofar as you're using vectors in the appropriate directions.
What do you mean?
Well, in this picture, I didn't tell you what is happening. For instance, this vector here.
This vector here?
Yeah, this one. Let's say there's a vector here.
Sure.
I can apply A to it.
Sure.
I didn't tell you what is happening to that.
Yeah.
We're going to get to that as well. Because here's the thing. And this is something that is also very useful. And this is why you can really sort of think of eigen spaces as one of these, like each one of these split colored lights, that V1 and V2 here are linearly independent, which means that they constitute the basis. That's called an eigenbasis. So that means that even if I have here sort of like some random vector, and I can't really say, oh, when I apply A to it, it's just going to be a constant multiple of it. I can still take my vector, split it into eigenvectors of A, and then see, oh, this component does this and this component does that. We're going to get to that. For now, let's just, this is just so that we're comfortable with computing things and the names. So let me again draw the spectrum and the eigenspaces. Again, I looked at this equation. This is now the eigenvector equation associated to the eigenvalue minus 4. I want a solution to this. And now I eyeball it. Yeah. You can do row reduction and so on, but and ultimately, if your matrices are large, eventually you're going to have to do some more calculations, but I am strategically using 2 by 2 matrices. So the spectrum of A consists of minus 7 and minus 4. And so the picture is like this. You see now both of them are outside. If this is 1, let's say this is 7, and now this is minus 4. Okay, and then My vectors are 1, 1, and the other one is 6 minus 5. So I guess I should draw it like this. One, 2, 3, 4, 5, 6. 1, 1, 2, 3, 4, 5. So that's V1. And then this is 6, and then this is minus 5. So that's V2. And again, I have two directions. So we can think of it like this. Just as in that case, I have two eigenvalues, and both of them are larger than 1 in absolute value. There's a minus here, but still it's going away from the origin, okay? And this is always being multiplied by 7, right? Because it's associated to 7, and this is always being multiplied by 4. So in a sense, whatever is happening along the direction of V1 is faster than whatever is happening along the direction of V2. So I can draw it like so. And instead of drawing that, I can just put arrows. And just so that it is clear that this V1 direction is faster, I'm going to put 2 arrows there. And here I'm going to put 1 arrow in one direction. Okay? Now, if I were to apply A to any vector here, it's going to be multiplied by 7, and it's going to keep going away from the origin. What happens if I were to take any vector proportional to V2 and apply A? Can you tell me what should happen? Yes, but what does that mean geometrically?
Well, it like goes the other direction.
Right? So it's going to jump to the other side. It's going to go away still from the origin. It's going to jump to the other side, and then it's going to jump to the other side again. Okay? Any questions about any two of these examples?
Is there any kind of physical example?
We're going to discuss dynamical systems a while later in week 13. So for instance, like prey-predator systems. Prey-predator systems. So you have two species, and one is the hunter, and the other one is the prey. That is modeled by essentially this framework. So the idea here again is that really I'm looking at not just A and what it does to one vector, but instead I'm looking at its powers. And now this n is my time. Just like in the case of shifts, in the case of signal processing, now my time is this power of A. And really applying A models progressing time by 1 unit. Okay.
Will that become more clear with time?
Say again?
Will that become more clear with time?
Yeah. And essentially, what we discussed in week 1, PageRank is also based on this idea. And this random surfer model, too. Any other questions? Okay. So now, yes. Oh, yes.
So when you say 7 times bigger than what the original vector was?
Yes, like A times V1 is 7 times V1.
Okay, so it's just 7 times of A.
No, 7 times the vector. So A times V1, or A applied to V1, which is this, complicated linear algebraic thing. It's really just scalar multiplication.
And then V1 is whatever we find.
Yeah, it's in this case, this particular vector.
So when we're talking about all this like eigen stuff,
Mhm.
like it's
Exactly. Yeah, so you see, before we had this null space and the column space and so on. Even there, we were sort of like switching our perspective from the vector space to the transformation. What is important is the transformation. It's not the vector space. So really, we want to sort of like split the vector space in such a way that the transformation becomes understandable. This is yet another example of this. So in the case of, for instance, the LU factorization, that's also another example of this. That is useful, but for the purposes of the column space and the null space, or rank and nullity. Here, you want even further information. You say, okay, so I don't really care about the column space, null space. I care about distinct directions that are invariant under A. So essentially, ultimately, I would like to be able to think of A as a diagonal matrix. The punchline here is that once you have this splitting, if you can figure out a nice change of basis, A becomes diagonal. So you're compressing information as well. Yeah.
So if you don't have, like, if you have a 2 by 2 matrix, and you can't find 2 distinct eigenvectors, does that mean that the matrix is like collapsing one of the dimensions?
Yes. What's an example to that?
Just like something that puts something on the x-axis, I guess?
Yes, a simple example for that is 1, 1, 0, 1.
Yeah.
You can go ahead and compute it, and we're going to spend more time on these like slightly more pathological examples, but we're starting with the case where you start with your matrix and you get distinct eigenvalues. Now, what's going to be a problem that we're going to have to deal with is that sometimes the eigenvalues are the same. You have repeated eigenvalues. Now things get slightly more complicated. Okay? So this is this notion of multiplicity. But before going into that, I have a couple minutes. I want to mention one more thing. Going back to this original example. Let me just remind you the example here. Well, maybe I shouldn't erase that. But I can just read it from here again. The first example was this. Three minus 2, 1, 0. Now, what is the trace of this matrix? Hmm? It's 3. It's the sum of the diagonals. What is the determinant?
It would be 2.
This expression is that, you see? This is called the characteristic polynomial of the matrix. And when you set it equal to 0, you get the characteristic equation. So char sub A of lambda equals this. For 2 by 2, there is also a characteristic polynomial for an arbitrary matrix, arbitrary square matrix, which we're going to discuss. But I just wanted to mention that you already had this, okay? And once you write this polynomial, so char of lambda equals lambda squared minus trace times lambda plus determinant of A, set it equal to 0, compute its zeros. Those zeros are going to be the eigenvalues of A, okay? You've also seen this polynomial in the context of the so-called Cayley-Hamilton equation in one of the previous problem sets, but we'll talk about that later, okay? So far, we just introduced this eigen stuff, and we're going to keep working on these. But I think it's a good place to stop. Thank you. Okay, let's start. Good morning. Yesterday, we were discussing something called the characteristic polynomial, and I wanted to talk about it more explicitly. The characteristic polynomial of a square matrix A, char sub A, and I'm thinking of this polynomial to have the variable lambda to be evocative, so the roots are going to be the eigenvalues, is nothing but the determinant of this matrix, lambda times identity minus A. Okay? And the characteristic equation is just char sub A of lambda equals 0. The roots of the characteristic equation of a matrix are precisely the eigenvalues. And this is a polynomial. It's always going to be a polynomial. And indeed, if your matrix is n by n, this is going to be a polynomial of degree n. And you see, this is why we were thinking of eigenvalues as complex numbers. Whenever you're trying to solve polynomial equations, it might be the case that you don't have real solutions, but you always have complex solutions. And that's why we're thinking of eigenvalues as complex numbers. Now, could you guess as to why it is the case that the roots of the characteristic equation are precisely the eigenvalues of A? Any ideas as to why this should be the case? Think of it like this. Yesterday, we were looking at this eigenequation, right? And I want a lambda, a number, and a vector, v, such that v is non-zero, right? And this has a solution. So v is a solution to this. And then we said, oh, I can send this to the other side and write it like this. Okay? And v, I want to be non-zero. I want it to be a non-zero vector. Well, if this is the case, it must be the case that this square matrix, which depends on this parameter, is not invertible, right? I'm saying that I want the nullity of this to be at least 1. Well, this can only happen if it is not invertible, okay? So the eigenequation for lambda, for fx lambda, can have a non-zero solution v only when lambda I minus A is not an invertible square matrix. And we know that this is the same thing as saying that the determinant of this is 0. Okay? So now you see, you can still, given a matrix, you can still go through this row reduction with parameters like we did yesterday to solve for lambda and v. But now this is a separation of concerns. Without worrying about finding solutions, finding eigenvectors, first you can write down this equation, the characteristic equation, and solve and find its solution lambda. And those solutions are going to be the eigenvalues. And then you can plug in the whatever eigenvalue you obtained to this equation, and then do row reduction to find an eigenvector for yourself. So here's an example for this. Yesterday we did only 2 by 2, but of course we can do 3 by 3 as well. So here's an example. 4 minus 1, 6. 2, 1, 6. 2 minus 1, 8. That's my matrix. Okay? Instead of doing this row reduction, I'm just going to look at the characteristic equation. The characteristic equation is nothing but 0 equals the determinant of this matrix, right? So I put lambda on the diagonals, and then I'm going to subtract each and every single entry of A from the corresponding place. So that's minus 4, 1, minus 6, minus 2, minus 1, minus 6, minus 2, 1, minus 8. Okay, so this is a determinant. Let's open it up. What was the rule? So this is plus. Let's remember. So plus. Need to write this out. And then another term is this. So 1 times minus 6 times minus 2 is 12. So that's a plus 12. Another term is this. 1 times minus 6 times minus 2 is again 12. So that's a plus 12 again. Now I have the minus terms. I have this term. So it's going to have a minus. So that gives me 12. So that's minus 12 lambda minus 1. And then the next minus term is this. So that's 2 times lambda minus 8. And then finally, I have this. So that's plus 6 times lambda minus 4. Okay? So this is the determinant of this lambda I minus a expanded out. And as you see, it's a polynomial in lambda of degree 3. So from here, I'm going to get a degree 3 term. And then and also I'm going to get a degree 2 term as well. And a constant term also. And here, I'm going to get degree 1 terms and constant terms. So let's write this down. Let's write this out. So continuing this way. So let me expand these two. So that's lambda squared minus 5 lambda plus 4 multiplied by lambda minus 8. That's 24. And then I can expand these. So that's minus 12 lambda plus 12. This is plus 2 lambda minus 16. And then plus 6 lambda minus 24. Let's expand this. This gives me lambda cubed minus 8 lambda squared minus 5 lambda squared plus 40 lambda plus 4 lambda minus 32. Okay, so now I have this remaining terms. I can try to consolidate a little bit. So if I were to take this and this, I get plus 36. And then if I were to take this and this, I get minus 40. And then I have minus 12 lambda plus 8 lambda gives me minus 4 lambda. Okay, keep going. So this is the third order term. My second order terms are only these two, minus 13 lambda squared. So I use this, I use this, I use this. So now I have the order 1 terms. 40 plus 4 minus 4 gives me plus 40. So I use this, this, and this. And finally, I have these. If I add these two up, I get 4 minus 40 minus 36. Okay? So based on this reasoning, it must be the case that whatever eigenvalue A has, they are exactly the zeros, whatever term, the zeros of this expression. You see, we started here from 0. Now, how to find roots of order 3 polynomials? In order 2, we know that there's this quadratic formula. In order 3, there's also a formula, but it's not as straightforward. It is slightly more complicated. What you can do is you can test out certain values. If you have, in this specific case, if you have a polynomial whose coefficients are integers, which is the case because we started with an integer matrix, then what you can do is you can test out factors, integer factors of the constant term. Okay? So the roots of this, the factors of this constant term are 1, 2, 3, 4. 5 is not, it doesn't divide. 6, and then the rest, right? So 36, 18, 12, that's 9, and then 6 remains. These are minuses, of course, plus or minus. I have all these candidates to find roots of this. And typically it's good to start with smaller numbers to compute. So for instance, if I were to plug in lambda equals 1, I get 1 cubed minus 13 plus 40 minus 36. Is this 0? It doesn't seem like it. Right, because I have minus 6 here. So that's minus 9. Yeah. So this doesn't work. How about minus 1? You see, I'm testing small numbers from these. My hope is that I'm going to get at least one root like this, and then I can factor out that factor. So if I were to plug in minus 1, I get minus 1. I'm plugging in whatever lambda value I have to this final expression. So that's minus 1, minus 13, minus 40, minus 36. Okay, so this is promising. But it's still not there yet, because this is a negative number. How about 2? Well, this is 8 minus 4 times 13 is 52. And then plus 160 minus 36. Let me see. Maybe I made an error. Probably I made an error somewhere. But oh, 80. Yes, that's true. Okay. Okay, so you see it works now. 88 minus 88, this is 0. Go fish. So you have it. Because this is a root of this, that means that char of lambda, which is that polynomial over there, maybe I should try it. So this is the characteristic polynomial. I don't need to write the subscript A because I have only one matrix in this case. Char of lambda is divisible by lambda minus 2. Divisible as polynomials. And so I can divide this polynomial by this to get a degree 2 polynomial, and then I can apply quadratic formula, whatever, to get the solution, get the rest. So how do I divide this? There are multiple ways of doing this, of course. You just pretend that this polynomial is basically a number, and you're trying to divide by some other number. So I want to get rid of this, which means that I need to use a lambda squared here. If I multiply, I get this back. Lambda cubed minus 2 lambda squared. Subtract. So now I have minus 11 lambda squared plus 40 lambda minus 36 left. So now I should be using minus 11 lambda minus 11 lambda squared plus 22 lambda. Subtract. Now I have 18 lambda minus 36. So that's plus 18. And you see, I have no remainder. That is to say, this characteristic polynomial splits as lambda minus 2 times lambda squared minus 11 lambda plus 18, which then I can split further into lambda minus 2 and lambda minus 9. You can again apply the quadratic formula if you want, but okay. So based on this, I have that one eigenvalue of A is 2, and the other eigenvalue of A is 9. Okay? So I can write it like this. Recall the spectrum of A was just the set of eigenvalues and I can write it like this. Any questions about this calculation?
So when we got like the characteristic polynomial, I know for like 2 by 2 there was like the formula was like lambda squared minus lambda trace the matrix plus the determinant. Is there something like that for 3 by 3 as well? Because 13 is the trace of that.
Exactly. Exactly. Yeah. No, it's not a coincidence. This second term, so this is always going to be multiplied by 1 when you write down the characteristic polynomial. This term is always going to be minus trace. And this term is always going to be determinant. Now, this term also has an expression, but we're not going to discuss that too much, but you can think of it as, so all of these are given by symmetric polynomials in the eigenvalues. So this is just the sum of the eigenvalues. We're going to get to that in a second. This is just a product of the eigenvalues. And this has to do with a linear combination of pairs, products of pairs of eigenvalues. Goes on like that. We'll talk about it in a second. But other than that, are there any other questions? I'm going to mention some shortcuts in a second, at least in 2 by 2, or some more structure. Okay, so we have this. So now you see we separated the concerns. We came up with the eigenvalues, and you see one of these eigenvalues is repeating. I get 2 twice in a sense. I have this second power. But when you look at the spectrum, obviously I have only 1, 2. Let me just go over there. Let's complete this calculation and come up with eigenvectors for the two eigenvalues. I have one eigenvalue, distinct eigenvalues. One eigenvalue is 2, the other one is 9. So I'm going to write it like this. Lambda 1 equals lambda 2, because I have two of them, okay, equals 2. Plugging this value into the eigenequation, I get this. So that was my matrix over there. So 2, 2, 2, and then I need to subtract the values. 1 minus 6, minus 2, minus 1, minus 6, minus 2, 1, 2 minus 8. Okay? So this is this lambda I minus A matrix. I'm trying to find a vector, non-zero vector, in the null space of this. That's what the eigenequation is. So let's write this out. You see, this is nice because the second and third rows are exactly the first row, which means that when you row reduce this, you get back this. Okay, now what does this mean? That means that any vector that is in the null space of this ought to satisfy this relation. So minus 2x plus y minus 6z equals 0. And I can say, for instance, y and z are free, right? If I'm thinking of x as sort of like the dependent one. Now, based on this, just as a reminder, sanity check, what is the nullity of this matrix?
2.
Yeah, right? The number of free variables is the number of is the nullity of the matrix. And so I get to choose two distinct things, okay? Two linearly independent vectors. And they are both going to be eigenvectors associated to this eigenvalue. Okay, so I'm going to have two eigenvectors associated to the eigenvalue 2. So let's choose some. I want to choose like nice ones, okay? So if I were to choose y2 and z0, or I can choose y0 and z1. And based on this, I want to figure out what x is. Well, if I plug in, I get minus 2x plus 2 equals 0. That gives me that x is 1. And if I plug in these other values, I get minus 2x minus 6 equals 0. This tells me that x has to be minus 3. So both of these are eigenvectors associated to the eigenvalue 2. They span the eigenspace associated to the eigenvalue 2 because they're linearly independent. And let's just check it super fast. In order for these to be correct, it must be the case that when I apply A to this or this, I should get back twice this matrix, twice this vector back. So, and this one. So my matrix was this. 6, 2, 1, 6, 2 minus 1, 8 times 1, 2, 0. Okay. 4 minus 2 is 2. 2 plus 2 is 4. 2 minus 2 is 0. You see, this is exactly twice the input. And likewise, if I were to apply the same idea to this other matrix, other column matrix, minus 12, 0, plus 6, minus 6. Let me just fast forward this. Okay. Now, yesterday we were only able to find one eigenvector that is linearly independent associated to an eigenvalue, but in this case we have more dimensions. Our matrix is three-dimensional, and we were able to find two linearly independent eigenvectors associated to the same eigenvalue, lambda equals 2. Okay? So we're still not done, because we need to compute an eigenvector for the other eigenvalue. I think at this stage I can, let me erase this piece. So lambda 3 equals 7, or sorry, 9. That's my third eigenvalue with, with multiplicity, right? So because I counted this twice, so this is lambda 3. Again, I need to do the same thing. Put 9s on the diagonal and subtract the entries of A. Oh, wait. Yeah, that's minus 4, that's plus 1, that's minus 6. Minus 2, minus 1, minus 6, minus 2, 1, minus 8. Now the new lambda I minus A is this matrix now. And again, I'm trying to find a non-zero vector in the null space of it. Let's organize this. Okay, so let's find a matrix for it. Let's find a solution to this. See, this is slightly more complicated, it seems. I hope I didn't make a mistake. So 1, 8, okay. I'm trying to see a pattern. If at all possible, I'd rather not solve it as usual and eyeball things, but I don't see anything. Okay, so now that means that we need to row reduce.
If you plug in 1 for each value, you get 0, I think, on the equation.
Oh, fair enough. Yeah. Okay. Okay. See, you guys are getting better at reduction than me. Yeah. So what it is that the third column is the difference of minus this and this, right? So if you take minus this and minus this, you get this. So if you do column reduction, if you want, you can get rid of this, and then you can do some more stuff. But in any event. There you go. this indeed, when you plug in, 5 plus 6 plus 1 is 6 minus 6 is 0. And then this is also 0. This is also 0. Thank you. So you see, this is an eigenvector associated to the eigenvalue 9. And we're done. That's the whole calculation of the eigenvalues and eigenvectors. Let me perhaps write this as well. I'll write some more stuff in a second. But maybe I can try drawing a picture. So we have this three-dimensional space, which I can interpret as the input or the output, or both, of A. I know that these two are linearly independent. Let me just stipulate that the third one, too, is linearly independent. And so what it is that I have these three vectors. Maybe they're not orthogonal, but or perpendicular. But it's hard to draw these vectors, so I'm just going to leave it as is. So v1 and v2 are associated to the eigenvalue 2. Just like yesterday, that means that any vector in their span is going to be scaled by a factor of 2 under A. If I apply A to it, it's going to be scaled by 2. So this plane is the eigenspace associated to the eigenvalue 2. Anything is expanding, but any vector that is proportional to v3 in the span of v3 is going to be expanded by a factor of 9 under A. Okay. Any questions about this?
Is there any reason how come you wrote like lambda 1 equals lambda 2 rather than just sort of like collapsing them into the same thing?
Yeah. So this was coincidental, but there are actually two types of multiplicities in place. One is this. The other one is the dimension of this. Okay? So I can say lambda equals 2 is an eigenvalue of multiplicity 2 because I have this power 2 here. Or I can say lambda is an eigenvalue of multiplicity 2 because the eigenspace is two-dimensional. Now this is coincidental. In this case, it turned out that both of these senses of multiplicity are the same, but in general, they can be different. And so the reason why I wrote it there is because I wanted to emphasize this. Okay? We'll see an example in a second, but let me just give the definition. Yeah.
Just for my own sake.
Yeah.
That algebraic multiplicity, like how we're used to, is not the same as there being two vectors associated with lambda.
No. I'll give an example in a second. Yes. Exactly. Any other questions about this? Okay. So let A be an arbitrary square matrix, and lambda be an eigenvalue of it. It's a number in the spectrum. Let me say lambda 0, okay? So the algebraic multiplicity of lambda 0, okay, is the largest power of lambda minus lambda 0 and the characteristic polynomial. Power of lambda minus lambda 0 in char. Okay, so in this case, the algebraic multiplicity of the eigenvalue 2 is 2, and the algebraic multiplicity of the eigenvalue 9 is 1. Okay, the geometric multiplicity of lambda 0, on the other hand, is the nullity of lambda 0 I minus A. Is in this case, the geometric multiplicity of the eigenvalue 2 is 2 because this is two-dimensional. And the geometric multiplicity of the other eigenvalue, 9, is 1. So it turned out that in this case, the algebraic multiplicities match with the geometric multiplicities, but this is not true in general. So here's an example for that. Let me go back to 2 by 2. And let's consider this matrix. Recall that this was a shear. Now, if I were to look at the characteristic polynomial, we had this simplification yesterday, or shortcut. But let's go through the motions and see that this is again computing the correct thing. I put the lambda on the diagonal, and then I subtract the entries of A. And then I take the determinant. That's it. So it has one eigenvalue, which is 1. Its algebraic multiplicity is 2. You see? So spec of A is 1. Let's say algebraic multiplicity of the eigenvalue 1 is 2, because it's the power. And I don't see any other eigenvalues. Let's try to find the geometric multiplicity. Let me do it here. So I need to do the following. Put the eigenvalue on the diagonals and then subtract the entries. Okay. Now this is 0, minus 1, 0, 0. And I want a matrix in the null space of this, but this has rank 1. Which means that its nullity is 1. Okay? So you see, the second coordinate has to be 0. Well, I can just take this. The nullity of this matrix is 1. You see, its geometric multiplicity. The geometric multiplicity of the eigenvalue 1 now is 1. Okay? Now, in general, algebraic multiplicity will always be larger or equal to the geometric multiplicity. So let me write it here. This is an important heuristic. So once you compute the characteristic polynomial, it tells you the maximum nullity of this particular matrix. Now, whether or not the maximum nullity is, or the nullity, actual nullity of that matrix is this algebraic multiplicity, that depends. You need to do further calculations. So let me write it like this. Algebraic multiplicity of any eigenvalue is greater than or equal to the geometric multiplicity of the same eigenvalue. Does this sort of answer your question? Yeah. Okay. Any other questions about this?
What do you mean by like lambda minus lambda 0? Like,
Where? Oh, here, lambda is my variable, is a variable for the polynomial. Lambda 0 is one of its roots.
Where the roots are one of the vectors we found?
One of the numbers we found.
One of the eigenvalues.
Yes.
okay, so so if I have lambda and then let's say for the other one we found like 9 was one of the roots, so you say like lambda minus 9.
Yes.
Oh, and then the number of times that shows up. Okay.
Yes.
Okay.
Mhm. Any other questions? Let me expand on this example, because we know that this is a matrix that belongs to a certain matrix group. It's a triangular matrix. It's upper triangular. If your matrix is upper triangular or lower triangular, or instead if it is diagonal, its eigenvalues are easy to compute. And here's how. Let's say that you have, let's use a lower triangular matrix this time. And I'm going to put lambda 1 to lambda n to the diagonal. So those are going to be the names of the diagonal entries to signal that really the diagonal entries are going to be the eigenvalues of a lower triangular matrix. So consider this. A is lambda 1, lambda 2, dot, 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 lambda n. Here, all entries are 0. Here, all entries are some numbers that I don't know. Okay? The claim is that the eigenvalues of A are precisely these numbers. Now, I'm not saying that these are distinct. Maybe some of them are repeating, but in any event. So let's look at the characteristic polynomial or the characteristic equation. So this is 0 equals lambda is a variable. Okay, lambda 1 to lambda n are fixed. Okay, now this is going to be 0, and this is going to be minus whatever junk I had here. But we know that the determinant of this is still lower triangular, as you see. Determinant of a lower triangular matrix is precisely the product of the diagonal entries. Okay, which means that the lambda 1 to lambda n, these diagonal entries, whatever they were, are the eigenvalues of A. Okay, this is just a more general case of what we did over there. The point is that I didn't need to compute all this. I know that A, just by looking at it, that A had the eigenvalue 1 as its only eigenvalue, and its algebraic multiplicity was 2. Okay. Of course, the same idea holds if I had started with a diagonal matrix. It's the same idea. the determinant of a diagonal matrix is the product of the diagonal entries, and you would get the same thing. Let me write that as well. Let me write it like this. The eigenvalues of A, which is the diagonal matrix with entries in the diagonal lambda 1 to lambda n. Maybe they are 0, maybe they repeat, I don't care. It's always, this is always going to work. The eigenvalues are lambda 1 to lambda n by the same idea. Okay, so this is like 2 shortcuts. Any questions about?
For that first one, that's a lower triangular.
Yes.
Is the same true for an upper triangular?
What do you think?
Yes.
Yes, right? Because the determinant of a matrix is the same thing as the determinant of its transpose. If you were to take an upper triangular, take the transpose of it, now it's lower triangular. Or you can compute, of course. Let me add one more thing. Let's just look at the 2 by 2 case again. You see, computing eigenvalues and eigenvectors is a chore, and you want to have as many shortcuts as possible. I'm just like telling a couple of tricks that you can use to fasten your calculations. If I were to start with an arbitrary 2 by 2 matrix, I know that its trace is the sum of the diagonal entries, and the determinant is AD minus BC. Now, if I were to look at its characteristic equation, I get this. Okay. So this is the trace, this is the determinant. Don't forget this minus here. But at the same time, if so in this case, I'm thinking of this as, as a polynomial, applying the quadratic formula, whatever, is always going to give me 2 numbers, possibly the same, but in any event, possibly they're complex. But in any event, I can write this degree 2 polynomial as lambda minus lambda 1, the first eigenvalue, times lambda minus lambda 2. Now, if I were to expand this to go back to that, you're going to realize that really determinant is the product of the eigenvalues, and trace is the sum of the eigenvalues. So that's another way of thinking about trace and determinants. Okay. Lots of material we covered today. Thank you. Tomorrow we're going to keep continuing on eigenvalues and eigenvectors. Okay, let's start. Good morning. Today we're going to keep working on eigenvalues and eigenvectors. So as usual, we're going to sort of open up the setting in a second. But before going into that, let's look at this example. This is a rotation matrix. And let's figure out the eigenvalues and eigenvectors. Well, let's use the standard rule. So I have lambda in the diagonals, and then I'm going to subtract the entries of A. And I'm looking at this determinant, and I want to set it equal to 0. Now this turns out to be equal to lambda squared plus 1. You see, this is why we're using complex numbers for eigenvalues. This polynomial doesn't split over real numbers. This is as far as you can go. But if you allow yourself complex numbers, you can go further. And by definition, we have that eigenvalues can be complex, so that's not an issue. So I can write it like this, right? Because plus 1 is minus I squared. Then I can split it. So I have, you see, complex conjugate eigenvalues. So I would write it like this. Spec of A is I or minus I. Okay? So if I wanted to draw the spectrum, now I would really use the imaginary axis as well, and I would put it like this, for instance. Recall that this was a complex plane. One eigenvalue is here, the other one is here. How about eigenvectors? In the definition, we also allowed eigenvectors to be with complex entries. And so I'm just going to go through the motions. There's nothing new happening. So for lambda 1, which is I, right? I plug in I, and then I have this matrix. And I want to solve this equation. Okay? So it's not as straightforward, perhaps, but the second row is I times the first row. So I can really look at this. Ix plus y equals 0. And y is free. That's a solution. And so for this, I can have, for instance, v1. So if I were to plug in x equals 1, y would be minus I. Okay? Let's check it. My claim is that if I were to take that matrix A and apply it to this complex vector, I'm going to get back this vector times I. So check. So 1 minus I. Now how do you do this multiplication? It's the same matrix multiplication. Now you just have complex numbers. So this by this plus this by this gives me I in the first entry. This by this plus this by this gives me 1 in the second entry. So this is... But note that this is nothing but I times this. So the eigen equation is satisfied. I'm using complex numbers and complex vectors, but still. For the other eigenvalue, note that minus I is nothing but the complex conjugate of this. Whenever you have a real matrix, it might have complex eigenvalues, but whenever you have one complex eigenvalue, its complex conjugate too will be a complex eigenvalue for the same matrix. So lambda 2 is lambda 1 bar. Bar denotes the complex conjugate. In this case, it's just minus I. And again, plugging in this value, I get this. Minus 1 and minus I here. And I'm trying to solve for x and y. Now you see, the first row is I times the second row. So I can, for instance, look at this. So this tells me that minus I times x plus y equals 0, y free. And what's the solution for this? Well, I can just use v2 to be 1i. Okay? Now note that just as the second eigenvalue was the complex conjugate of the first eigenvalue, whenever you have an eigenvector associated to a complex eigenvalue, its complex conjugate, which you do by entry-wise, is going to be an eigenvector for the complex conjugate of the eigenvalue. So this is nothing but E1 bar. Okay? So the underlying idea here is that so let me just write it here, perhaps. A can be any matrix with real entries, and I look at this. Let's say that this has a solution. Well, surely if I were to take the complex conjugate of both sides, I can rearrange things. That's the idea. So lambda bar times v bar equals lambda times v bar equals a times v bar equals a times v bar. Okay? So that's why if this is the case, then so is the case, and vice versa.
What enough? A bar times B bar?
Exactly, but a bar is a. Right? Because it doesn't have any complex entries.
When you say complex conjugate, do you mean like if you add them together, you get rid of the complex part?
I mean by the complex conjugate, so a plus ib bar equals a minus ib. Complex conjugate in the sense of one of the previous problem sets. There was a problem, recall. So let me write it like this, bar, and then a v bar. That's the underlying idea. Now, what are the multiplicities of these eigenvalues in this case? Well, I has algebraic multiplicity 1, minus I has algebraic multiplicity 1 also. When it comes to geometric multiplicity, however, there is some confusion about what to call it, but based on what we defined, since we don't have any eigenvector that is completely with real entries, all eigenvectors have complex parts, I would say that the geometric multiplicities of I and minus I are both 0. Because I don't have this null space. So let me record it here. So in this case, the algebraic multiplicity of I and the algebraic multiplicity of minus I are both 1. And the geometric multiplicity of I and the geometric multiplicity of minus I are both 0, based on our definition. Okay? I should say that these are also, of course, dependent on this field of scalars that you're using. But in this class, we're not really discussing that too much, and this is sort of like a technicality, so I don't want to spend too much time on this. Any questions? Geometrically, you should think of it like this. I mean, we know that this matrix is a rotation, of course. It's a rotation by 90 degrees in the counterclockwise direction. But whenever you have a square matrix, with real entries, say. And whenever I, or it has an eigenvalue that is complex, that is an imaginary part, that should signify for you that when you apply your transformation to whatever space you have, there is some rotation happening. Okay? So the existence of complex eigenvalues should indicate that there is some rotation happening. Let me write that as well. I'm going to write it here. Some rotation, some kind of rotation. Now, in this case, everything is being rotated this way, and it's an orthogonal transformation. And so circles are going to stay as circles. Okay, but maybe if you have a different eigenvalue, it might be sort of, the rotation might be along ellipses, or maybe it's along spirals. These things happen. Especially, for instance, if you take an introductory class in differential equations, this is one of the things you end up needing to study quite a bit. But in this class, I don't think it is that important. Maybe once we start talking about dynamical systems, which is going to be in a couple of weeks, I think, maybe we can discuss that a little bit more. So this is that. As you see, somehow, because ultimately you're using a polynomial to find out about the eigenvalues, complex numbers just creep in naturally. Okay, any questions about this? Yeah.
So, this is more so just brushing up on the multiplication.
Yes.
When you did the row reduction to get that,
Yes.
-1 times I is negative I, or is that positive I?
-1 times negative I is positive I.
-1 times. Okay.
Yeah. It's just like regular addition and multiplication and everything. The only rule is that you have this new symbol I, such that its square is -1. That's the only difference. Yeah. Okay. So now let's go to the abstract setting. If I were to have an arbitrary vector space V and a linear transformation from V to itself, I can again look at this equation, eigenequation. This makes perfect sense, and I can try to solve it for lambda and V. Obviously, in the general case, it's slightly more complicated to solve it, possibly. But still, it makes perfect sense, and it is very useful. And on top of that, if the dimension of your vector space is finite, then indeed I can bring in all these tools that we've developed so far, characteristic equation and so on. We're going to get to this part in a second. First, I want to give a couple examples of the first piece, because that is also very important. And this is one of the reasons why linear algebra is very useful. So for instance, consider this. Differentiation is a linear transformation from the space of differentiable functions to itself, and I can ask what are its eigen vectors. I should say, in this general setting, often depending on whatever type of vector you have, you call instead of eigenvector, you call eigen that other thing. So in this case, instead of saying eigenvector, you say eigenfunction. Okay. And for instance, eigenvalue also has specific names depending on the setting. In this case, sometimes you might hear the word energy. So if your vectors are functions, then your eigenvectors are eigenfunctions. So what are the eigenvectors of D and eigenvalues? Well, all I need to do is to write it like this, right? So this is f prime of t equals lambda of f of t. Now this is what is called an ordinary differential equation. This is one of the main undergrad classes. Does any of you have any guesses as to what f should be here, if I were to give you this? So it's a function that if I differentiate it, I get back the function itself up to a constant. Exponential functions, yeah, right? So you can do calculus and stuff like that as well. But so c times e to the lambda t. Okay, so this is telling you, and I didn't tell you what lambda is. Any number is an eigenvalue of the differential of the derivative operator, and here's an eigenfunction. Okay, and in fact, I can say that the eigenspace for any eigenvalue is one-dimensional because any eigenvector or eigenfunction associated to lambda is a constant multiple of e to the lambda t, this exponential function. So spec of D is actually everything. You see? And so let me just leave it like this. There's another example, for instance, this is also very important. You look at the eigenequation for second derivatives. This is differentiating two times. This is a differential operator or linear operator in its own right. And so now I'm writing like this. So this is f prime double prime equals lambda times f. This, for instance, represents what is called the harmonic oscillator that is free and undamped. So you have sort of like a spring and it is oscillating, there's no friction, and there's no external force. You're not doing anything to the system. So people typically write it like this. Instead of lambda, they put here omega squared, because the solutions of this turns out to be in the span of cosine of omega t and sine of omega t. So this omega is the frequency of your oscillations. This omega is the frequency of your oscillations, and this is all there is to it. Now, if you take 2250, 2280, or whatever, some other differential equations class, you spend quite a bit of time in this because this harmonic oscillator is a very important thing. But in this case, it requires some constructions, let's say. So I just wanted to mention that it is relevant, but I don't want to go too much into detail. So this is, let's say, harmonic oscillator that is free and undamped. So no friction and no external force. Then the solutions of this tell you whatever function represents your oscillation. How about this one? We had this R operator on the space of all functions, which just reflected. Along the y-axis. What are the eigenfunctions of this? So I need to write it like this. So lambda times f. Certainly, lambda equals 1 has solutions. Those solutions are called even functions. And lambda equals -1 also has solutions. Those solutions are called odd functions. So any even function is an eigenfunction of reflection associated to the eigenvalue 1. And likewise, if I were to plug in -1 here, that would correspond to odd functions. Any odd function that is non-zero, of course, is an eigenfunction of R associated to the eigenvalue -1. Does this make sense? That's literally how you define an even function. You say, I have this operator, which is reflection, and I want, so I define an even function to be any function such that when I reflect it, I get back exactly the same thing. That is literally saying that even functions are eigenfunctions associated to the eigenvalue 1, and so on. So there's still this issue of whether or not, in this stage, lambda can be some other value. Maybe there's some other value such that this eigenequation can be solved. Okay, so this is one solution. So one eigenvalue is this, another eigenvalue is this. I'm asking, are there any other lambdas for which there's an f? You see, in this case, you don't have something like a characteristic polynomial, so it's not as straightforward as to how to even answer this. But you can think of it like this. Now, say I have this equation. I don't know what lambda is. I know that f is not a zero function because eigenvectors, eigenfunctions, are not zero functions. Well, if I were to apply r 2 times, I get back to identity transformation because reflection is like this. So if I reflect 2 times, it's the same thing as not doing anything. So f is equal to I times f, which is the same thing as r squared of f, which is the same thing as r applied to r of f. But this is, if f is a solution to this, lambda times f. R is a linear operator. Lambda is a constant. I can take it out. Now I can apply again. So f has to be equal to lambda squared times f. Okay? So lambda squared minus 1 times f of t equals 0. This is a non-zero function, which means that this has to be 0, which means that lambda can be only 1 or minus 1. Okay? Of course, there's nothing special about this particular vector space and this particular linear transformation. In order to deduce this, maybe you can guess, what type of a property did I really use? So if I wanted to abstract this out, this idea over here, how would I go about doing this? So say I have an arbitrary vector space and an arbitrary linear transformation, I'm looking at the eigenequation for it. And I want some condition on my linear transformation that would allow me to pretty much write this down and say that, oh, any eigenvalue of this transformation is either +1 or -1. Well, the only thing that I'm really using here is that r squared equals I. That's called an involution. Let me write it. A linear transformation whose squared is the identity transformation is called an involution. So T from V to V is called an involution if T squared equals identity. Now you're going to realize that if you start with this, the same argument that I wrote over here is going to apply. The one problem is that maybe it is not true that originally you have a solution. So I don't know in general if both +1 or -1 is going to be an eigenvalue, but I know that if I have an eigenvalue, it has to be +1 or -1. So let me leave that as an exercise for you. If lambda is in the spectrum of an involution, then lambda in absolute value has to be, well, I can say it better like this. Then lambda is +1 or -1. Okay. And in particular, for instance, I can think of the operation of taking the transpose, acting on a space of square matrices. That's an involution because the transpose of the transpose is not doing anything. It's an involution. In which case, I have that the only two eigenvalues of the operation of taking the transpose is are either 1 or -1. We can also compute it, of course, but okay. Any questions about? Yes.
How did you go from like lambda squared f means that lambda squared -1 times f of t equals 0?
Okay, because f is supposed to be an eigenfunction. So in particular, it's an eigenvector. Eigenvectors should be things that are non-zero. So when I'm looking at this, I'm really looking at non-zero solutions, v. What does it mean for a function to be non-zero? It means that there is some time value t such that f of t is non-zero. Plugging that t value in this equation, that would give you a non-zero number. But this has to hold no matter what t is, which means that this has to be 0.
Yeah, but like how did, I guess I'm asking, how did you go from lambda squared to lambda squared -1?
Oh, because lambda squared times f is equal to f.
Oh, yeah. So you're almost like factoring out of
Yeah.
lambda squared.
Yeah.
Or you're factoring out f,
Um,
I guess.
I mean, what do you mean by that?
Like you can, if you say like f equals lambda squared f, then you can move that over. You say lambda squared minus f equals.
Yeah. Oh, yeah. Of course. Yeah. I mean, if you want, this is also axiomatic, right? Because I have one vector here and then a scalar multiple of the same vector. One of the axioms was that I can add or subtract in my field of numbers, and that would distribute. I can think of it that way as well, but of course this is true. Okay, any other questions about this? Let's do another example. Now, in the case of the signal space, shift transformation, recall that this was defined like this. Rho of x at n equals x of n minus 1. The terminology in this case is eigensignals. And instead of eigenvalues, sometimes people use the word gain. Okay. So what are the eigensignals and eigenvalues, eigensignals and gains of the shift operator? Well, again, I need to set up the equation. Rho of x, I want to be equal to lambda times x. Lambda is a number. So what does this mean? This means that, maybe I should write it using the ticker tapes. So I'm going to compare x, rho of x, and lambda x. Okay, so this, synchronize. And I don't want to keep track of the 0 time in this stage. I want to start at an arbitrary time n. So this is x of n plus 1, x of n plus 2, and so on. So this first ticker tape corresponds to the signal x. The second one I want to correspond to rho of x. What should I write here in this box? This is not p, it's rho. It's just the shift. It is defined like this. It's the shift operator. Exactly, right? The rule was that you take it, move it this way. So this is x of n plus 1, x of n minus 1, x of n minus 2, x of n minus 3, and so on. And let's say in the third row I have lambda times x. Now what does this mean? It means that I need to scale whatever entries I have by lambda. So I'm going to have here lambda times x of n. So I start with this, I scale it by lambda, I get back this. Lambda times x of n plus 1, lambda times x of n plus 2, and so on. In order for x and lambda to be a solution for the eigenequation of the shift operator, then it must be the case that this is equal to this for any n. I think I can erase this. So need x of n minus 1 equals lambda times x of n. Okay? So now for any n, so now what I can do is the following. I can say, okay, so if lambda were 0, this would be 0. So no matter what n is, the left-hand side would be 0, which means that x would be the 0 signal. I want a non-zero solution. That's always the case for eigenequation. So that means that lambda equals 0 is not an eigenvector of rho. So 0 is not in the spectrum of shift. It's not an eigenvalue. But if I were to start with a non-zero lambda, then what is happening really is that, so I can write it like this, right? So I can send this to the other side as a division. It's like this, which itself is, so this x of n minus 1 is 1 over lambda times x of n minus 2, and so on. Which means that, you see, if I were to choose x of 0, the value of your signal at time 0, some non-zero number, then I would get a constant multiple of the exponential signal. That's what we call. Because x of n is, you know, it grows or decays depending on what lambda is.
After lambda, so on your second row, and then it points to x of n equals 0.
Right, because if x of n minus 1 equals 0 for any n, it must be the case of x of n is 0 for any n.
I guess how does that relate to lambda equals 0?
Well, if lambda is 0, this is 0. I'm saying x of n minus 1 equals 0 for any n.
Okay. So I guess that's why I'm confused. Shouldn't it be x of n minus 1 instead of x of n in that second?
I'm changing the variable.
Okay.
If for any n, x of n minus 1 is 0, it is also the case that for any n, x of n is 0. Yes. I mean, write down the ticker tape, right? It's like, I'm saying that if lambda were 0, x of n minus 1 is 0 for any n. So this is 0, this is 0, this is 0, this is 0. No matter what n is, it is 0.
Okay.
That's literally the 0 signal. It's your 0 vector. Yeah. So in this case, in the second case, when lambda is non-zero, x is a constant multiple of an exponential signal. Okay. So in this case, what is the spectrum of rho? It's everything, so it could be complex as well. It's everything but the origin. So it's a complex plane except the origin. Okay. Now, this is an important thing because in general, if you have an operator, if you have a linear transformation or a square matrix, we know that its determinant, or let me say it this way. If you have a square matrix, we know that it is invertible if and only if its determinant is non-zero. But at the same time, determinant is the product of eigenvalues, which means that a square matrix is invertible if and only if 0 is not an eigenvalue of it. It's both way. It's both ways. Yeah. So if I have an n by n matrix, I know that A is invertible if and only if determinant of A is 0, not 0, but determinant of A really is the characteristic polynomial of A evaluated at 0, right? Because determinant of A is the same thing as determinant of 0 times identity minus A, which is the characteristic polynomial of A evaluated at 0. That's the constant term of your characteristic polynomial. And we know that this is the product of eigenvalues, of all eigenvalues. Which means that determinant is going to vanish, or it's going to be non-zero. Let's say determinant is going to be non-zero only when 0 is not an eigenvalue. So 0 is not in the spectrum of A. So if you know that you have a certain matrix that is square, and you know that it's not invertible, and I'm asking you to come up with an eigenvalue of it, you can literally say 0 has to be an eigenvalue. Okay? This is also very useful, of course. Question?
So
Yeah.
that, just to be clear, that's determinant of 0 times A minus A. Or sorry, times I. 0
Yes.
times I minus A.
Yes. So this is a 0 number. So instead of lambda in the characteristic equation, I put lambda equals 0. So now let's talk about diagonalization. Diagonalization is about a change of basis that is admissible in certain situations. Of square matrices. Let's do it like this. Okay, I'm going to give a definition. So let's let A and B be arbitrary square matrices of the same dimension. Let's say n. And I'm going to call them similar, or conjugate is also another word, if the following happens. If there is some other square matrix P that is invertible, such that I'm going to go up. So I'm going to put it like this. Okay? So P, B, P inverse, which is a product of 3 n by n matrices, I want that to be equal to A. I'm not saying what P is. I don't ask if it's unique or whatever. I'm just saying that A and B are related like this. When they are related, I'm going to call them similar. And a good way to think about this is using, so thinking of A, B, and P as transformations, and then I can think of it like this. So Rn, 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 and in order for this to happen, so A should be the same thing as this, so P goes up. Okay, that's another diagram. Okay, and in this case, so taking a matrix and multiplying it from the left and from the right like this is called the conjugation. So you're conjugating the matrix B. Okay, and when you can get, so whatever other matrix you get by conjugating a matrix is called the conjugate of the matrix B. So here's the important thing. If two matrices are similar, then, well, for instance, the determinants are the same because determinant is multiplicative. So the determinant of A would be the same thing as the determinant of P times determinant of B times determinant of P inverse, which you know to be the reciprocal of determinant of P, which means that I would get back determinant of P. And likewise, you did this in the previous problem set, trace would be the same as well. More generally, if two matrices are similar, their characteristic polynomials are equal. Consequently, their eigenvalues are the same, their spectrum are the same. Not necessarily their eigenvalues, but still, sorry, not necessarily their eigenvectors, but still they share something, okay? Char sub A of lambda is the same polynomial as char sub B of lambda. Consequently, spectra are the same. So spec of A is the same thing as the spectrum of B. And for any shared eigenvalue, the algebraic multiplicities would be the same, and the geometric multiplicities would be the same as well. Now, why is that? It all comes from this, essentially. So let's write it out. Okay. By definition, char sub A of lambda is lambda times identity minus A, but A is that, and I can write this like this. So P lambda I, P inverse is the same thing as lambda I, minus A is the same thing as this. Simplifying this, I get this. Determinant is multiplicative. Determinant of P times determinant of minus P, P inverse is 1. So this just gives me the char sub b of lambda. Okay.
Where did the p lambda I p inverse come from?
So take this, do this multiplication. Because this is a scalar, I can move it anywhere I want.
Gotcha. Okay, and I is inverse and is similar to itself?
Yeah. But so I is identity with respect to multiplication. So it's I can just pretend it's not there. Yeah. Okay. Thank you. We're going to keep working on this on Friday. Okay, let's start. Good morning. Today we're going to keep working on eigenvalues and eigenvectors and everything. One important topic is this idea of diagonalization. So today we're going to start talking about that. So recall that we had this definition of similarity. We have two square matrices of same dimension n, and I call them similar if one is a conjugate of the other one. Recall that that was sort of the name for it. So A equals PBP inverse for some P invertible matrix, again of the same dimension. And if you want, you can also think of that equation in terms of this flowchart or diagram. The notation for similarity is this. Right? You want to say A is kind of like B. They're not exactly the same, but similarity is important because if you have two similar matrices, then their spectral data are the same. So the characteristic polynomials are the same. We discussed this last time, which means that the spectrums are the same. So the spectra are the same. The eigenvalues are the same. And further, because this is a polynomial and so is this, the algebraic multiplicity of any eigenvalue relative to A should be the same as the algebraic multiplicity of the same eigenvalue relative to B. And of course, trace and determinant are specific coefficients inside these characteristic polynomials, and these numbers are the same as well. Further, if I were to take an eigenvector V associated to lambda, right? That's the null space of lambda I minus A is the eigenspace associated to lambda. So if I were to choose a vector from that eigenspace that is an eigenvector, then P inverse V is going to be an eigenvector corresponding to the other guy. So here's how we can see this. So I'm going to do it here. Saying that V is in the null space of this matrix is the same thing as saying that A times V equals lambda times V. But I know that A equals PBP inverse. Which means that if I were to take this P to the other side, I would have this. P inverse A equals B P inverse. Okay. So now I can apply P inverse to this equation, and I would get this. So lambda times P inverse times V equals P inverse times lambda V, because lambda is a constant, it's a number. Now, lambda times V is equal to A times V. But then P inverse times A is the same thing as BP inverse. So you see, I started with the eigenequation for A, and I said, oh, let's say that V is a solution to this. Then I realized that P inverse V is a solution to the eigenequation for B. Okay? And of course, I can rewind this argument and say, oh, if I were to start with an eigenvector for B, I can rewind this argument, and P times that eigenvector would be an eigenvector for A associated to the same eigenvalue. Okay? So of course, the vectors quite possibly change. V is not the same thing as P inverse V, but still, P is an invertible matrix, and that means that dimensions are preserved. In particular, the geometric multiplicity of any eigenvalue relative to A is going to be the same as the geometric multiplicity of the same eigenvalue relative to the other transformation. So similarity is very good in that regard. And all the spectral data, algebraic multiplicity, geometric multiplicity, whatever you can think of, they are all preserved. Any questions about this so far? I'm dumping some background material, but in a second we're going to start doing specific examples as to why this would be useful. This is just symbol pushing at this stage. Now, note that if then I were to start with a general finite dimensional vector space and a general transformation T from V to itself, certainly I can turn it into a matrix by choosing bases, right? I can choose two bases, beta and gamma, and I would have two matrix representations of the same transformation. What is interesting, though, is that these matrices, they may not be the same, but they're always going to be similar. Which means that even though you really need this crutch of choosing a basis to really start doing these calculations, at least for finite dimensions, whatever you end up with will always be relevant. So it's not going to be whatever you end up with, the eigenvalues, eigenvectors, they're not going to be because of the specific basis you chose. It is basis independent. So the eigenvalues, eigenvectors, eigenspaces, these are in the things themselves. It's not about how you look at it. Okay? And so why is this the case? Well, think of it like this. Really, P there, you should really think of it as a passive transformation. So somehow I should be able to, so I should use this change of basis matrix from beta to gamma to turn this into that, or vice versa. And so here's what you can do, for instance. You can say that this really is this. Okay? So this matrix, the matrix of T relative to the basis beta, is really this product. So this is the change of basis matrix from gamma to beta. This is this other matrix relative to the basis gamma. And then this is the change of basis matrix from beta to gamma. So if I were to call this A, for instance, or maybe I should call this B, and if I were to call this C, and if I were to call this P, P for passive, it's a passive transformation, then this should be P inverse. So you see, we do indeed get this. That is to say, one matrix of the same transformation relative to some basis is not the same but similar to another matrix with respect to another basis of the same transformation. Okay? And you can just draw, if you want, the universal diagram, or you can sort of like calculate things. It's somewhat of an exercise to verify that this is indeed the case, but for our purposes, this is all you need to understand. When I'm looking at this equation for similarity, really I'm thinking of P as a passive transformation. P, this invertible matrix, over there even, corresponds to a passive transformation, really. And really, when I'm seeing this similarity relation, I'm thinking of A and B as the representatives of the same transformation. Same underlying transformation. So maybe I should leave that as an exercise to you. So this is exercise. And so based on this, you call a transformation diagonalizable if it has some matrix representation relative to some basis that is diagonal. But perhaps before even writing that, let me write this. We mentioned this in class, but I want to be explicit about it. If I have a matrix and if I have eigenvectors associated with distinct eigenvalues, then those eigenvectors are going to be linearly independent. Say I take p many distinct eigenvalues, and I don't want these to be zero vectors, they're eigenvectors, be such that A times vi equals lambda I vi. What I said is the following. I said that if these eigenvalues are distinct, then these, the eigenvectors, associated eigenvectors, are linearly independent. There's a proof in the book, and it's a nice idea, of course, but maybe it's not very illuminating to go through the proof, but maybe if you have time later, we can discuss this. What this means is that if I tell you that A is a 2 by 2 matrix, it has two distinct eigenvalues, by definition, for each of those distinct eigenvalues, you're going to have one eigenvector at the very least. And without checking, you're going to have that those eigenvectors are linearly independent because they correspond to different eigenvalues. Okay, so this is very powerful. And based on this idea, if indeed you have sufficiently many eigenvectors, then your transformation is what is called diagonalizable. So let me write it like this. T is called diagonalizable if there is some basis that I'm going to denote by epsilon, relative to which the basis, the matrix of T is diagonal. If there is a basis epsilon of V such that the matrix of T relative to epsilon is diagonal. And whenever you can find such a basis, the reason why I'm calling it epsilon is because that basis is an eigenbasis. Any vector in that basis would be an eigenvector. Is an eigenvector. Okay? So here's an example. Of course, the world would be unfair if diagonal matrices or transformations that already start as a diagonal matrix were not diagonalizable. So indeed, diagonal matrices are diagonalizable. Right, so So for instance, if I were to start with, let's say, 1, 1, 2, 3, that's a 4 by 4 matrix. The standard basis of your space, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1, right, would be an eigenbasis. Okay. So here's a slightly more complicated example, and this is where this idea of diagonalization really starts to shine.
So the column, you're saying the column vectors of D?
You can think of it that way as well.
That would be the eigenvectors?
Yes. Yeah. I mean, I can use the column vectors, or I can use the, just ones and zeros if I wanted, right? Because this is, of course, 1, 0, 0, 0, right? And I multiply, because multiplying D by this is the same thing as looking at the first column. But if I were to, for instance, look at this, this is the third vector in the standard basis. Well, this is this one, 0, 0, 2, 2, 0, which is twice the input. So it's an eigenvector. That's the beauty of diagonal matrices, in a sense. So, okay, so here's a more complicated example. Because it might be the case that you're given a matrix which represents a transformation, and initially it doesn't look like it is a diagonal matrix. The point is to be able to change the basis so that with respect to that new basis, your matrix really is, your transformation is really represented by a diagonal matrix. So here's an example. Let's say that we start with this matrix. Okay, so this is not a diagonal matrix. Okay, so the question is it diagonalizable? The way to answer this is by going through the motions, computing eigenvalues, eigenvectors, and so on. So let's look at the eigenvalues. Recall that we put lambda on the diagonal and then subtract the entries of A. And I want this to be equal to 0. Now when I expand this, I get this. Lambda minus 7 times lambda minus 1. And then minus 8 plus 8. Yes. Expanding that, I get lambda squared minus 8 lambda plus 7 plus 8 plus 15. Okay? Which should be indeed the case, because we know that in the case of 2 by 2 matrices, the characteristic polynomial should be lambda squared minus trace times lambda plus determinant. Trace is indeed 8, and the determinant is 7 plus 8, 15. So it is okay. And you see this splits it into lambda minus 5 and lambda minus 3. Which means that I have two distinct eigenvalues. And based on this, I can say that A is diagonalizable. The reason why is this. You see? I know that I have two distinct eigenvalues, which means that I'm going to be able to find, I didn't find it, but I'm going to be able to find an eigenvector for 3 and another eigenvector for 5. And based on this, that eigenvector for 3 and eigenvector for 5 that I will compute are going to be linearly independent automatically. Okay? Which means that these two eigenvectors will be an eigenbasis. Which means that based on my definition, if I were to use that basis, the transformation that would represent this would be diagonal. Okay? So this is the prediction. Let's go through the motions and really see that this is indeed happening. So maybe I should record it over there, or over here. Since A has two distinct eigenvalues, by, let's say, this statement by star, there are two eigenvectors, let's say v1 and v2 of A. So v1 corresponding to the eigenvalue 3, v2 corresponding to the eigenvalue 5, that are linearly independent. Well, I know that R2, which is the vector space A is acting on, is two-dimensional. And if I have two vectors that are linearly independent, they must constitute a basis, which means that v1, v2 gives me really an eigenbasis. And so I have this new basis that I came up with. The idea is that when I do this change of basis, whatever it is that I need to compute, I will get a diagonal matrix, and the entries of the diagonal are going to be exactly 3 and 5. Okay? Now, this diagonal representation of the transformation is not unique. Okay? The numbers in it are unique, but maybe, so using some other situation, I could have put 5 here and 3 here. I chose to put 3 here, 5 here. But so permuting the eigenvalues is the only choice you can have when it comes to the diagonal representation for a diagonalizable matrix. So let's figure this out. So you see, at this stage, I know that there's an invertible P, that change of basis matrix that I haven't computed, but it is there, right? Yeah, so A equals P 3, 5, 0, 0, P inverse. And of course, at this stage, if you wanted, you could plug in values for A, you know, the entries of A, and you can say, oh, let me start with an arbitrary matrix P, A, B, C, D, and, you know, do this equation, solve this equation, and it would also solve. But there's a slightly better way of doing this. And that goes through computing eigenvectors. I really want what these eigenvectors are. So lambda 1 is 3, okay? And the other eigenvalue is 5. Okay, so I have 3 on the diagonals, and I need to subtract entries of A. So that's minus 7, minus 2, 4, and minus 1. Oh. What is this? This is minus 4, minus 2, 4, 2, which is similar, or row equivalent, let's say, to 2, 1, 0, 0. So V1, the eigenvector corresponding to 3, I can choose as, for instance, x1, y minus 2. Okay, and as usual, let's check, because we're still getting used to this. So the claim is that if I were to take A, multiply this column matrix by A, I should get back 3 times the same matrix. So 7, 2, 1 minus 4, 1 times 1 minus 2 gives me 7 minus 4 is 3, minus 4, minus 2, minus 6. This is indeed 3 times this. Okay, so it works. Doing the same thing with the other eigenvalue, I get this. So that's now minus 2, minus 2, 4, 4. Now this is row equivalent to 1, 1, 0, 0. So as V2, this eigenvector associated to the eigenvalue 5, I can choose as 1 minus 1. And again, let me leave it to you, or maybe I should do it. Let's again check that it is indeed an eigenvector associated to the eigenvalue 5. So I need to do the following. Take this matrix, multiply it by this. Now you see 7 minus 2 is 5. Minus 4, minus 1 is minus 5. This is exactly 5 times this. Okay?
From the matrix, say 2, 1, 0, 0 to the V1 equals 1 minus 2.
Yeah, I eyeballed it. Okay?
Sorry?
I eyeballed it. So, because the point is to find the null space of 3i minus a. Find a vector in the null space. That's what it means for a vector to be an eigenvector associated to 3. Now, I computed this matrix. This matrix is this. Okay, so the equation I'm trying to solve is this times some vector equals 0. Okay, so now this becomes this, and then this row reduces to this. So the second row doesn't give me any information. The first row tells me that 2x plus y equals 0. What is a choice for it? It's like integers. I like using integers. Yeah. In 2 by 2, it's like you can eyeball it. When the dimension of the matrix gets larger, it becomes harder to eyeball things, of course. And the same here, same idea here. Now I'm looking at the null space of 5 times I minus a. Same idea. Any other questions? Now note that this statement over here already guaranteed for me that v1 and v2 were going to be linearly independent. And if I were to look at this, 1 minus 2 and 1 minus 1, they are linearly independent, right? Because if I were to look at the 2 by 2 matrix whose columns are this and this, it's going to be invertible. Its determinant is non-zero. Let me call that matrix P. Recall, even before doing all these calculations about eigenvectors, I knew that there was going to be a P like this. The point is figuring it out. So we have again separated the concerns. One concern is whether or not a matrix is diagonalizable. The other concern, which is much more specific, is what exactly the similarity matrix you should use as the P to get that diagonal form. So if I were to put P to be V1, V2, this is a 2 by 2 matrix. Oh, this goes over here and this goes over here. Its determinant is -1 minus -2, which is +1. Okay, so it's not 0, which means that this is invertible. Now here's the idea. Okay. I'm thinking of this as some sort of universal diagram as well. And so here I have R2. And I'm thinking of matrices as transformations. So if I start with 1, 0 down here, P would take it to the first column, which is 1 minus 2. Now A would take this to 3 times it, which then P inverse would bring down to 3 times 1, 0. So whatever this matrix is, the first column of it should be 3 times 1, 0. So 3, 3, 0. And if I were to use the other one, by the same idea, now because I'm plugging in 0, 1, this would zero out the second column, so it would give me 1 minus 1. Applying A to it would give me 5 times 1 minus 1, and then P inverse would again bring down to 0, 5. So whatever this missing matrix is, its first column ought to be 3, 0, second column ought to be 0, 5. That's a diagonal matrix. Okay? And so if you take this matrix, and you can go ahead and do this calculation as well, you're going to realize that if you do this calculation, you get back A. So you would be successfully diagonalizing A. Okay? Questions about this?
What's the symbol next to the 1 and 2? So it says P equals 1, 1 over above.
Oh, this is like, I'm trying to say, P is that matrix whose first column is V1. So it's like a, yeah. And the second column is V2.
I see.
Yeah. Now, what is the standard operating procedure then? When it comes to a question regarding whether or not a certain matrix is diagonalizable, first step is to compute eigenvalues. If you can find distinct eigenvalues, so whatever the dimension of your space is, if you have n dimensions, you need n distinct eigenvalues, then you're automatically good to go. If not, you can still go further and compute eigenvectors, and if you can find linearly independent eigenvectors, in other words, if you can find an eigenbasis, then putting those eigenvectors in a matrix like this and interpreting it as a passive transformation would produce for you this diagonal matrix, so that you would be able to diagonalize. So that would be sort of successfully diagonalizing a certain matrix. Yes?
So is your eigenbasis this, the 3005, or is it going to be?
The eigenbasis is going to be this vector and this vector.
Okay.
Okay, so here it is.
Okay.
Yes.
Are they just put in as vectors, or do
So a basis is by definition an ordered tuple of vectors. So that's why I'm calling it. But you see this, so you can interpret a basis as sort of like a tuple of vectors, or it's a change of coordinates also. You can interpret it either way.
Okay, so then the A that's equal to P times RD P1,
P inverse.
what is that saying? What's that called? What's the label of it?
That
It's the equation of what?
this is the equation for similarity.
Okay.
I was able to find a matrix that is similar to A that is diagonal.
Okay. And
That's
then
what-
you can plug any P and P inverse in and it
That's the point. Once you have this, P and P inverse have to be, so there is some freedom, but you would need to use here an eigenvector associated to this eigenvalue. Okay, so the first column of your P is an eigenvector associated to the first eigenvalue here. Second column of P is an eigenvector associated to the second eigenvalue here.
And that's why the other diagonals are zeros because they don't really matter. Because it's just based off of the eigenvalues.
Well, yes, essentially.
Okay.
So here's another example. Not all transformations are diagonalizable. So for instance, if I were to take this, this matrix turns out to be not diagonalizable, which means that there is no basis consisting of eigenvectors of A. A doesn't have sufficiently many linearly independent eigenvectors. So here's how we can do this. At first stage, of course, you need to compute the eigenvalues, but we know that upper triangular matrices have their eigenvalues on the diagonal. So spectrum of A, the space of, or the set of eigenvalues, consists only of 2. It repeats. Now I'm trying to find eigenvectors. Okay, I have one eigenvalue, which means that any eigenvector should be associated to this. Okay, so lambda 1 equals lambda 2 equals 2. Now I want to find eigenvectors for this. Put 2 on the diagonals and then subtract the entries of A. Zero minus 1, 0, 0. Now just as in this case we were computing a vector in the null space, or as many vectors as we want, in the null space of this lambda I minus A matrix, here too we're trying to compute a matrix. We're trying to compute a vector in a null space of 2I minus A. And so I'm setting this equal to 0 and I'm trying to solve it. Well, this is, so the second row is not telling me anything. The first row is telling me that the second component of my eigenvector is always going to be 0, which means that I can only use something like 1, 0. So you see, the algebraic multiplicity of the eigenvalue 2 is 2. It repeats. But the geometric multiplicity is 1. Okay? So I don't have any other eigenvectors. Any other eigenvectors I could come up with will be proportional to this guy, which means it's not going to be linearly independent from this. Which means that this matrix doesn't have any eigenbases.
So it can only be an eigenbases if there is more than one eigenvector.
Linearly independent, yes.
Linearly independent.
Yes. Has no eigenbasis. so A is not diagonalizable. Okay. Now, maybe I should give this as an exercise. You can figure this out in a different way. You can say, okay, so let's say that I start with A, and I want to find a B. So let me write it like this. Exercise 2102 equals P, and then I want to have a diagonal matrix, and in the diagonal, I'm always going to have the eigenvalues. So the diagonal has to be the 2002 matrix, and then P inverse. Well, if you have a 2 by 2 matrix, you have the formula for P inverse of it, so for the inverse of it. So you can say, let's say P is ABCD, plug in the values, multiply this, equate. You're going to be able to see that this has no solution. This is also a very concrete way of doing this, but you really need this technology a little bit, because as you can imagine, when it comes to higher dimensional matrices, even in 3 by 3 matrices, you're going to have sort of like P and then P inverse, and it's going to be a mess in a sense. It's going to be hard to figure out whether or not a certain matrix is diagonalizable purely based on this equation for similarity. So it's better to go through this eigenvalues, eigenvectors, and so on, and figure out if you have an eigenbasis. Yes?
So you can have a matrix that has only, like, let's say I have a 2 by 2 and you have only one eigenvalue.
Yes.
But you can still have 2 eigenvectors that are linearly independent, right?
Yes. What's an example for that?
We did one, I think, right?
If you started with 2 times identity, that would be an example for that. It's already diagonal.
Yeah.
Okay. The only eigenvalue of it is 2. It repeats. Its algebraic multiplicity is 2. Its geometric multiplicity is 2. Well, why is that the case? Geometrically speaking, 2 times identity does exactly the following. It takes the whole plane or any vector in the plane and expands it by a factor of 2. It does everything. So it acts this way everywhere. So that's sort of like the geometric interpretation of this. Any other questions? So maybe I should write down this standard operating procedure. Diagonalizability. So standard operating procedure for diagonalizability. Diagonalizability. Step 1 is to compute eigenvalues. Meaning, compute a characteristic polynomial. Let's say that we have an n by n matrix. If you have n distinct eigenvalues based on what we discussed, then this matrix is for sure diagonalizable. If n distinct eigenvalues, distinct and real eigenvalues, then A is diagonalizable. On the diagonal, so this diagonal matrix, is going to have the eigenvalues of A. You don't know what this P is at this stage, but at the very least you know that it is diagonalizable. Now I'm not saying that if you don't have distinct eigenvalues, A is not diagonalizable. An example for this is this. If you have possibly repeating eigenvalues, you need to keep going. You need to compute more things. So this is the simple case. If you have distinct real eigenvalues, you're good. It's diagonalizable. If not, you have to keep going. Or if you want to compute that P, that conjugation matrix, that similarity matrix. Step 2 is compute bases for each eigenspace of A, which means to find bases for null spaces of certain matrices. So for instance, null space of 2i minus a and so on. Plug in the eigenvalue on the diagonal, subtract values of A, and then you solve it. So let's say that if the sum of all geometric multiplicities, so the sum of all dimensions of eigenspaces, equal n, the space of so the dimension of the total space, then it is diagonalizable. If not, as in this case, not diagonalizable. If geometric multiplicities add up to n, then A is diagonalizable. Hey, let me just write it like this. Otherwise, A is not diagonalizable. Okay, so this is the first routine. This is about diagonalizability. Now the second question is, often you're going to get, like you're going to have a question like this: is A diagonalizable? If so, diagonalize it. To diagonalize a matrix, first go through this standard operating procedure, figure out that it is indeed diagonalizable, then do this. It's the size of, so n by n is the size of my matrix, or n is the dimension of my space. So standard operating procedure for diagonalizing a matrix A. Step 1, figure out if it is diagonalizable. If it's not diagonalizable, there's nothing to do, of course. Let me not write that down. If it is diagonalizable, so let me write it like this. If A is similar to a diagonal matrix D, then take the linearly independent the eigenvectors that you computed in item 2 above. Put them in a matrix P. Step 3, you're guaranteed that this equation is going to hold. Is guaranteed. Okay.
For the 3 on the first board, it says if the geometric multiplicities add up to n, then A is infinity.
Yes.
It says so, and above that it says compute the bases.
Yes.
Is it essentially just the amount of bases? Does the count of bases add up to n? In which case it is diagonalizable.
Yes.
Okay.
Yes, because so each of these eigenspaces are subspaces. You can talk about bases of it. And you can take, so if you have a bunch of eigenspaces, take a basis for this, take a basis for that, and so on, put them together. If ultimately you end up with a basis for the whole thing, then it is diagonalizable. Otherwise, that means that there's some vectors lacking somewhere, as in this case. The geometric multiplicity is less than algebraic multiplicity somewhere, in which case it is not diagonalizable. Yeah. Any other questions? This is involved. Like, I mean, it's not that involved, but it takes a while to get used to these calculations and stuff. Okay. This just about covers most of the things I wanted to discuss. There's, on the syllabus, if you look at it, there's something called the Gershgorin theorems. Maybe we're going to cover this later, toward the end of the semester. This is sort of like a bunch of theorems that allow you to approximate eigenvalues by just looking at the matrix. It's very useful, but we'll discuss it later, possibly. Thank you.